Welcome to Topology Lesson 7 on metric spaces, definition and examples. This is the first in several lessons on the topic of metric spaces. After I give you some introductory information on this lesson, I'll proceed to talk about concepts like open and closed sets, compact sets, connected sets, and so forth. And that'll take us into several more lessons beyond this one. High-level definition of a metric space is a set of elements, also known as points, along with the concept of distance between any 2 points. The set could be an infinite set, and the distance is measured by a function called a metric or a distance function. Many of the properties associated with metric spaces can be developed without the concept of distance in the more general context of what are known as topological spaces. So we'll talk about those after I finish with the lessons on metric spaces. So we have an example here. Euclidean n-dimensional space is a metric space. We can use this as a distance function. It's just a square root, and then you take the difference between the first dimension and then the elements of the second dimension, and all the way up to the elements in the last, and you square each one, add them together, and take the square root. So you would notice this in R2. Actually, I do it for R1 here, but let's do R1 first. So if you just have a line in a one-dimensional space, then you have the square root of just, your x1 minus y1. I just did x and y here, squared, and this is by definition the absolute value. For a two-dimensional space, I can maybe just wipe this out. So for two-dimensional space, you have just two elements, one for each direction, and then it would just be this familiar formula which you've hopefully have seen before. That's just the distance between 2 points in R2. And of course you could do it in R3, and you would have one more element in that case. Formal definition of a metric space is a set of points and a distance function. And the distance function maps between an ordered pair where both elements are from the set of elements, so m by m, and it gets mapped to a real number. So the distance between an element and itself needs to equal 0 in order to be a metric space. In fact, all four of these need to hold true. So that's kind of an obvious one. Then the distance from x to y, where x doesn't equal y, is greater than 0. Then you have symmetry. The distance from x to y is equal to the distance from y to x. So if we let's just say that's a two-dimensional space, and we have an x at one end and y at the other end. Then we're just saying that the distance from x, let me do the pointer here, distance from x to y is the same as the distance from y to x, so there's a symmetry. If this is a one-way street, then the distance from x to y is some given distance, but then you can't go back in this direction, so it's not even defined in that case. So that would be an example of where the distance function doesn't work. Then you have this triangle inequality where the distance from x to y is less than the distance from x to z plus the distance from z to y for any z in your set. So if we go back to our example here with the two-dimensional space R2, and let's say we had a z up here, then it's just saying the distance from x to y is less than the distance from x to z plus the distance from z to y. So in the case of two-dimensional space, it's kind of obvious. It's just saying that the shortest distance between 2 points is a straight line. But we'll see some other examples where this triangle inequality is not so obvious. And I already mentioned this, the distance has to be finite. This is just by the definition because you're mapping to the real numbers. And then you can also take a subset of M, or in this case I used X here. So you have a metric space X and D, and if you take a subset of X, Y, then you can define a restriction of your metric to Y, and then you have this metric space Y, D prime, where D is this restriction, and that's called a subspace. On this slide and the following slides, we have several examples of metric spaces. The first one is based on something called the Chebyshev distance, and for that you take elements in r-dimensional Euclidean space, which we write as Rn, and the distance between two elements is the maximum distance between the components of each element. I'll show you an example in a second. Excuse me. And in terms of a metric space, if you have the same X and Y, then all of their components are the same. And of course, that would give us a 0. So that holds. And if there's any difference between the components, when you add when you take the max, you're going to get a positive number. So that's greater than 0. Symmetry holds because symmetry holds for the absolute value. X minus Y is the same as Y minus X when you're taking the absolute value. And the distance function of the triangle inequality holds because it holds for at the absolute value of two numbers, difference between two numbers. So we have that here. Now let's take an example. If n is 3 and we have three-dimensional Euclidean space, and take two elements from that, so that's our X and Y here, and then our X1 and Y1 are 1 and 2, and the difference is 1, and then X2 and Y2 are 2 and 4 respectively, and that this difference is 2. Then we take the difference between the last components, and that's 3, so that would be the max 3. And so the distance between X and Y for these two things is 3. Another example is the taxicab distance, and instead of taking the max, you take the sum over the absolute value of the component. So like if we had this thing here, we would have 1 plus 2 plus 3, so we would get 6. So these 2 points would have a distance of 6 using the taxicab distance. And the metrics space conditions hold. If the two components X and Y are the same, then these are all different. These are all the same too, and you just sum them up and you get 0. If their X and Y are different in any component, you're going to get a positive number here, and then so that's greater than 0. So that's the second one. Symmetry again holds because of the symmetry of the absolute value, and this for the same reason the triangle inequality holds, because it holds for the absolute value of the difference of two real numbers. And I'll actually show you an example of the taxicab distance when n is 2 in the next slide. Then we have the discrete metric, which is pretty simple. So you can take any set, doesn't have to be Euclidean space like we had in these two examples. It could be any set, and we define the distance between two elements in the set to be 1 if the elements are different, and 0 if the two elements in the set are the same. As I mentioned on the last slide, we have something called the taxicab metric, or the taxicab geometry. And here's an example in two-dimensional space. You can think of this as a street grid in a city and the taxi cab distance is the red here. So it's basically the difference in each direction. And you can go this way. This would give you the same distance. You notice if you're just looking horizontally, you have this plus this plus this plus this. These all add up to that, and then the up steps, these add up to this here, and then here's another example where you would get the same distance. So there's multiple ways of getting between these 2 points in a taxi cab, and they're the same distance. What's not allowed, or what doesn't fit into this metric, is the Euclidean distance. That would be the straight line, but of course you can't do that if this is a street grid. So I just put it here to emphasize that we're showing two different metrics here. This is the Euclidean distance in R2, and then this is the taxi cab distance. Now the other point I wanted to make is this is assuming the streets are all bidirectional and it's the same distance, and whatever metric you're using to define distance between, say, these points on the grid. So for example, maybe this is a one-way street going this way, but when you come back, maybe you have to go this way, and then maybe these streets don't work and you have to actually go out this way and then come back. So it could be longer. And anyone who's driven in a city knows that you might be able to get between 2 points quickly, and then coming back it's longer, or vice versa. So in that case, you will not have a metric. So taxi cab geometry implies or assumes that you have a bidirectional. Otherwise, you don't get you don't satisfy the metric space requirements. So we have a few more examples on this slide. The first one is based on the Hamming distance, which measures the number of variances between two strings, and that gives you the distance. So it's kind of a simple idea. If you have strings based on digits and letters, like I have here in this example, then you have x equals, say, this string, and y equals this string, and in bold I've highlighted where they're different. So you have up to v, dkm, v, they're the same. Then 4k, k4, is different from I7, and then the next 5 numbers are the same, but then the last 2 are different. So this string differs from this string by 4 in 4 places, and that's the Hamming distance. So that's actually a metric space. You could define it on any set of characters, numbers. It's most typically used as binary, so you just have strings of zeros and ones, and then the Hamming distance is how many places where the two differ. And that's used in error correction and detection. So if you sent one binary string and then you receive it altered, and let's say it's altered in 3 places, some error correcting codes will correct all errors up to 3, some will go up to 4, and so on. And that's the typical usage of this Hamming distance. So we have another example here that's quite different from the ones we've seen. It's the set of continuous functions on a closed interval AB, for example, 1, 2. And if you take 2 functions in that set, then the differences, or the distance between the 2 is defined as the integral of the difference of the absolute value from A to B with respect to x. And this holds true, the metric conditions hold true, because if f equals g, then of course this is 0. If f and g are not the same over some subinterval, then it's going to be greater than 0. Of course, if you get into the complexities of measure theory, they could be different on a measure of 0, in which case the integral would still be 0. But I'm not going to get into the details of that. Let's just say that if these two are different, you're greater than 0. And The symmetry holds because symmetry for the triangle, the absolute value of the difference of two numbers holds. So if we had this equals the same as the absolute value of g of x minus f of x. And then because the triangle inequality holds for the difference of two real numbers, it holds for this this integral here. So we have a metric space. And we have a generalization. Instead of this simple integral, we can raise the absolute value to the p power, where p is a real number greater than or equal to 1. Of course, when p is 1, we get this case. And then you take the power 1 over p of the entire thing. The triangle inequality for this is harder to prove. It's based on Minkowski's inequality, which is discussed in an associated Wikipedia article, but I'm not going to go into the gory details here of that. In this example, we take the set of all n-dimensional complex tuples. So we have x1, x2 up to xn, where each element is a complex number. Remember, complex numbers are numbers of the form a plus bi, where a and b are real numbers and I is the square root of -1. In fact, if you download my book, the final chapter in the book goes into great detail on complex numbers, and we won't go into very much of it here. I just want to show this as an example. So you can define a matrix here, which looks similar to what we had in the previous slide, except it's a summation now, and the difference between two elements from C to the N, Cn, is the summation. You take the absolute value of the difference between each of the terms, each of the elements in the set here, raise that to the p power, add them together, and then take 1 over p root of the entire summation. And that, again, is a metric space. The first three things are conditions are kind of obvious. If these are exactly the same, then this is 0. If they're not the same, you're going to get something bigger than 0. Symmetry holds because of the absolute value. And the triangle inequality, again, is not easy to show, but it's based on the Minkowski inequality, and which I mentioned before. That's that inequality is, there's a whole Wikipedia page on that, so you may want to have a look there if you're interested in the details. Let R infinity be the set of infinite sequences. So basically this set here, where you have x1, x2, x3, you have an infinite number of terms, and they're one element of your set, and each of the components is a real number. And then we can define the metrics being the distance between x and y for two elements from this set is the sup or supremum of the absolute value of the difference between the components. So if you are not familiar with sup or supremum, I have a little bit of an example here. First, the definition. So the supremum of a subset of a partially ordered set P is the least element in P that is greater than or equal to every element in S, if such an element exists. So we'll make it a little more concrete. Let's say our P is the set of real numbers, and S is this set here. So this is 0. If you put in n equals 1, you get 0. N equals 2, you get 1/2. You put in 3, you get 2/3. You put in 4, you get 3/4. So you get a sequence of numbers starting from 0, 1/2, 2/3, getting closer and closer to 1. So the sup of this set S in P equals the real numbers would be 1, because it's the smallest number in R that's bigger than every number in our set S. But the maximum of S doesn't exist because S doesn't include 1 itself. So that's the reason you use sup here, that you can have a set that has a sup within the larger containing set, but that sup is not an element of the set itself, so it doesn't have a maximum, or it doesn't contain its maximum. So sometimes you'll see sup used instead of max. And same thing, there's a infimum and a which is used instead of min for the similar reasons. Okay, we have another example here of if we take any set S and the set of bounded real functions on S, then we can define the metrics D, F, G, so the difference between F and G, two functions in this set, as being the supremum of the difference, the absolute value of the difference between the two functions over the set S. And that'll give us a metric space. Okay, one more example. This one's kind of complicated. The reason I put it here is, and the reason it's in my book, is the second chapter of the book is on non-Euclidean geometry. And again, you can download that book freely, but I talk about the Poincare disk there, and I didn't actually get into the distance function when I first introduced it. So later on in my book, when I got to metric spaces, I decided to put it in here. So it may or may not make sense, given that you may or may not have read the first part of my book, but that's okay. Let me just kind of give you a high-level view of what's going on here. So the disk model, all your points are on a disk. And if you take 2 points inside the disk, your P and Q, there's a unique hyperbolic line that goes through those 2 points, and it intersects it meets the tangent line here at a 90-degree angle, and the same thing here. So just take it for granted that there's a single line that goes through here. Then to define the distance between P and Q, there's this rather complex function that the inventors of this particular geometry came up with, and it's the distance between P and Q is the log of this complicated thing, where D sub 2, I put the 2 here because it's the Euclidean distance in R2. And so if you compute this, it turns out this is actually a valid metric, and it works on this Poincare disk model for hyperbolic geometry. So a little bit complicated. It's okay if you didn't follow. The point I wanted, this is the last example in this here, but the point I wanted to make, and the reason I went through all these examples, I'm not going to take these examples as I go forward for the most part, but the point is that all the theory that we develop, and what I'm going to have in the next few slides is just a small part of what you can develop for metric spaces, but all those theorems that you're going to see hold for any of these metric spaces. That's the point. It's not just two-dimensional space, Euclidean space, or n-dimensional Euclidean space. It's for a rather large set of examples that work. And just think, if you had to prove all those, I don't know how many I have, let's say a dozen or so theorems, if you had to prove each one of those for each example independently, not realizing there's a common structure called the metric space. So that's the value of defining these common structures. You can prove theorems based on the conditions of the metric space, and then those theorems hold for every possible example, some of which we haven't even been discovered yet. So that was the point. Hopefully it wasn't too torturous and you understood most of the examples I went through here, but some of the main ones are the Euclidean space that we'll go back to, and others as needed we'll bring them up again. Okay, so the next several lessons will be on various concepts like open and closed, and sets, and associated theorems for those type of sets.